それでは次の講演を始めさせていただきます。続いてはフランケンスタイン、フルスタックファジングによる組み込みファームウェアと Android のバグの発見について、ヤン・ルージュさんからご紹介をいただきます。ヤンさんはドイツ・ハンブルグ大学でコンピューターサイエンスを学び、セキュリティの道に入った方です。世界のハッカー会議のルーツでもあるドイツ CCC の CTF チーム、WOD の中で CTF のチャレンジを構築してきた経験を持ちます。ヤンさんからは今回のテーマについて動画をいただいておりますので、どうぞご覧ください。
Hi, welcome to this presentation, Frankenstein, Uncovering Bugs in Embedded Firmware and Android Full-Stack Fuzzing. My name is Jan Ruge, and in the next 30 minutes I want to show you how we use firmware emulation as well as firmware patching to find bugs in Bluetooth. So first off, a quick motivation. Radio protocols by their nature have a huge attack surface, so any nearby attacker can always try to attack with them. In this research we are focusing on Bluetooth, especially on the unauthenticated attack surface. So for example, if you have an Android device and Bluetooth enabled, anyone who knows your Bluetooth address can connect to your device and start to exchange, for example, L2 card messages with your device, and those are even processed by the operating system. In addition, there are some protocols that are terminated within the firmware and hidden from the user, and this is something we wanted to have a closer look at. So why do we want to use emulation? Well, reverse engineering is hard, especially on embedded devices. In the case of Bluetooth, we have very strict timing constraints, so we can't easily set a breakpoint and trace the execution, because this would alter the timing behavior and as well as the behavior of the firmware. In this particular case, we had a 2 megabyte large firmware and around about 300 functions that are somehow related to packet reception, but we have no idea how those are invoked, in which context they are called, what are their arguments. Usually this is just a pointer of some sort of struct. And if we perform emulation, we can trace the execution, we can see the arguments, and we also have to focus on the code that is actually executed to understand it. This is a target device that we have used. It's a Cypress Bluetooth Low Energy development board. So we can execute our own C code on the controller. And the cool thing here is that there is no separation between the firmware and the application. So within your C code, you have full access to the whole RAM, for example, and you can even perform modifications to the code stored in ROM to some extent. In addition, does the IDE leak symbol names for basically everything? So we know the function names, we know the global variables, we know the name of the hardware registers, and this made reverse engineering far more efficient. Now a quick overview of what Frankenstein is. The core concept of Frankenstein is to write C code in the context of arbitrary memory images. So in the case of our Bluetooth development board, we want to obtain a memory image, reassemble it on the host, and write C code in the context of this memory image, so we can, just as you would normally do in C, dereference pointers, call functions, etc. So we have something like a symbol database where we have all our symbols that can be managed. And in the compilation step, you can either compile patches, what are basically tiny shellcodes that can be pushed to the device and executed, or we can compile it to an ELF file that can then be executed in QIM-ARM, for example. Most of the tasks in Frankenstein are performed using hooking. For example, we can replace functions, or we can print debug messages if a particular function was called. So first off, how do we obtain the memory image? On the right, you can see the code how we did this. So we have this xmit state function that will save all the registers to the stack, and then calls xmit memory, and this will then send a memory image to the host. Important here is that we must disable interrupts, so there's no code executed while we dump the memory, because this would alter the state. And in addition, it's quite important to directly use the hardware registers, for example, for the serial interface. So we don't need any functions that invoke state machines, etc. Once we have the memory image on the host, we just have to jump to the continue label, which will then restore the stack pointer, restore the registers, and continue execution. So this memory, or this binary dump, has to be somehow compiled to an ELF file, for example, for emulation. And down here you can see the linking process. So on the left we have the firmware with all the memory regions, and we call xmit state and end up with several binary dumps of those memory regions. And those are then converted into object files, so they can be passed to a linker. And then we have our C code that we write. We compile it also, and then we link this all together to an ELF file. For this, we have two linker scripts. One defines all the symbols in the memory image, like this one above. And the segments.ld describes the final memory layout. So we end up with an ELF file that has the same memory layout as the firmware, but there is an additional page that contains our code, where also the entry point is located. So if you execute this ELF file, first our entry point is executed, and then we can perform modifications to the code stored in the ROM. For example, install hooks, disable functions, etc. And in the second step, we call the continue function to continue execution. So now I want to give you a quick overview on how the Broadcom Bluetooth firmware works. The firmware is essentially divided into two parts. A part that is based on ThreadX, what is a real-time operating system, and a Bluetooth cross scheduler, what is a custom scheduler developed by Broadcom to handle Bluetooth time-critical tasks. On the right, you can see a diagram of the firmware with the host. So if you already have some experience with Bluetooth, you might know L2COP, what is basically the lowest layer protocol that you normally speak between two devices. This is directly passed through the firmware. Then we have HCI, what is the protocol spoken between the host operating system and the controller over a serial interface. And those messages are first of all received by the BT transport thread that implements a state machine to handle the serial interface. And once those messages are received, they are passed to the link manager, what is the most complex task thread inside the firmware. And this thread also handles something that is called the link manager protocol, LMP. This protocol is used to establish pairing, for example, or to handle the connection setup. And down here we have the Bluetooth cross scheduler with various different Bluetooth-related tasks, for example, Bluetooth connections, paging, device inquiry, like scanning for devices, etc. So first of all, we have to take care about the multi-threaded operating system. But if you first execute the firmware, you will run into a function that will throw an illegal instruction. For example, there are functions used to enable and disable interrupts within ThreadX. And those do not work on a Linux operating system, so we just have to override them with a plain return, so the execution continues. And for the multi-threading part of ThreadX, we had to re-implement one function called tx thread system return, what performs a context switch between two threads. This is normally invoked as a software interrupt, like or supervisor call. And as this concept doesn't exist on the Linux operating system, we had to re-implement this function, what was run about 50 lines of assembly code. And if we have all of this set up and continue the execution of the firmware, we can observe several context switches until we end up in the idle thread, and the idle thread will then finally perform a return from interrupt. So this means that in this point of the firmware we were called from an interrupt and we have returned from the interrupt, so we can now with no worries call new interrupt handlers. So the way how we did this is we have overwritten this return address on the stack with our own function that is then called. And in this function, we can then invoke new interrupt handlers to trigger new behavior. And this preserves all of the multi-threading of the firmware, so this is completely untouched. And yeah, that was quite nice. For the Bluetooth core scheduler, this was a little bit more tricky because this is invoked around about every 300 microseconds. And the reason for this is in Bluetooth we have discrete time slots, each is around about 600 microseconds long. And the Bluetooth core scheduler invoked by the Bluetooth core interrupt is actually called twice for every time slot. And this is also the earliest entry point for packet or for received packets into the firmware. So this is a really good entry point for fuzzing. In addition, at this point in the firmware, we have full access to the packet and the payload header that are prepended to the payload. So if you're normally using Bluetooth and send L2 card messages, for example, you only have control over the packet payload. And even inside of the link manager, you only have control over the payload of LMP messages, or it's just a different packet type. But from the Bluetooth core scheduler, we have full control over the headers and can modify them. And this will be interesting later on. So here is a slide with a lot of code, and this is how we inject raw wireless frames into the firmware. So it's basically the invocation of the Bluetooth core interrupt. But first of all, I want to explain you the calling convention, so this does make more sense. As mentioned before, the Bluetooth core scheduler is invoked twice for every clock cycle, and here's the reason why. So if the lower 2 bits of the Bluetooth clock are, for example, 0, we have received the header of the packet and the payload header of the packet. If the Bluetooth clock is 0-1, like at the end of the time slot, we have received all the packet data. And there are several other states where, for example, for transmission, and those are used for scheduling the Bluetooth tasks. The Bluetooth core interrupt is controlled by a hardware register called FuseStatus. And as we do not have any, and this is normally set by the radio front end, but as we do not have the radio front end, we have to take care of this on our own. So if we now have a look at the code, first of all, here on the top there is a Bluetooth core, the Bluetooth clock, sorry. And this is normally also incremented by the hardware, but as we have no hardware, we have to increment it on our own. And the rest of the code is essentially just we are checking the lower 2 bits of the Bluetooth clock, and if those are 0, we are calling receive header done. And this is the step where we have the packet, where we have received the packet and payload headers, and we just perform like a Linux read system call to set the value of those headers. If we have 0-1, we're performing a read operation on the received buffer. And here we set the various other different states. And in the end, we are calling the Bluetooth core interrupt. And this just executes in an endless loop. So to give you a quick summary, what we have accomplished so far, we have support for threading. We can also inject HCI messages. We can inject and extract raw wireless frames. So what we now can do is we can attach the emulated firmware to a Linux operating system, pass data into standard in, and the firmware will try to process this data as it were with valid wireless frames. And also we have added a lot of debug output. And this is something I want to quickly demo you. So here we are on an Ubuntu. As you can see, we have currently no Bluetooth adapter. And if I execute this here, we have just the data2 file just contains random data. And here we have our emulator. And as soon as I execute this, you can see we have now an adapter that goes through the various initialization steps. And now it's an inquiry scan, so we are scanning for other Bluetooth devices. And the firmware will try to pass the data that we passed to it as they were scan results. And as you can see, we even get scan results here in our UI. And in this particular case, the firmware crashed. And the reason for this is that we have added an additional feature that I haven't shown you before, what is a heap sanitizer. So we are checking the heap integrity, for example, after each and every mem copy. And in this particular case, it has detected a heap corruption. And this is really cool because if you normally overwrite data on an embedded controller, you have essentially no possibility to break at that point where you have corrupted the data, because you can't really set breakpoint on memory accesses. However, in this particular case, the execution is aborted as soon as the memory corruption occurs, and we have the debug output and can now go through this and see what's happened. So as you can see here, we have a memory allocation of hex 109 bytes. And later we have a mem copy into this buffer of something that is obviously larger. So this is a valid memory corruption that has been triggered. And we can even see that we are coming from this function here. So we can go to this function in IDA and see what's happening. So in this particular case, this is not a bug of our emulator. It was a real bug inside the firmware. And this memory corruption roughly affects 8 to 10 years of production of Broadcom and Cypress controllers. We are not sure because the earliest firmwares have no build date in them. And we have, just for fun, developed the full remote code execution exploit against this. And the interesting part here for you is that this bug is actually located in two different components of the firmware. So one is the Bluetooth core scheduler that is affected, and the other is the link manager. And here's the relevant code. So in the Bluetooth core scheduler, we tried to get the packet length from the payload header. The definition on the payload header you can see here on the bottom. So first of all, we are discarding the lower 3 bits, and this is okay. And then we apply a bit mask to mask out the length. And in the link manager thread, we are performing a mem copy operation using the previously computed length. The problem here is that the bit mask over here includes the RFU field, the reserved for future use field. This is normally set to 0 because it's reserved for future use. So this is normally not has no impact. However, if an attacker sets one of those bits to 1, we can greatly exceed the final length of the buffer here. And you should notice that the receiving hardware just ignores the firmware, and the firmware should that the receiving hardware just ignores this field, and the firmware should also ignore the field, but it doesn't, and therefore we can trigger here a memory corruption. We had some trouble with the disclosure process, so in the end we're escalating this directly to the vendors. For example, to Google, they have published a fix in August 2019. And also to Apple, who gave us public recognition. And if you are interested in why this is actually exploitable, down here is a link to the write-up. Now I want to talk about Bluetooth connections, or ACL. So ACL was our main goal to fuzz, especially ACL and the link manager protocol. And we tried really, really hard, but failed also really hard. So we tried coverage guided of fuzzing of one LMP messages, of multiple LMP messages, of the emulated firmware with attached to blues. We tried coverage guided fuzzing of ACL, and we couldn't provoke any crash, which was quite surprising because the link manager that we are targeting here is by far the most complex component of the firmware. And just to be on the safe side, we also developed a patch that lives here in the Bluetooth core interrupt that will mutate packet data essentially before they are sent out. So we can just run an L2 ping flood to the target, and the controller will then send corrupted packets to the target, however with the correct checksum. But well, Anyway, we didn't observe any crash, except one weird thing during the time we are working on the Nexus 5, because we had already put a lot of effort in understanding this particular firmware. And for some reason, I managed to crash the Bluetooth daemon using this fuzzing approach I described earlier to you. The problem here is that Android itself wasn't really in scope. I had no time to debug this. As you can see, we had no symbols available. It's a heavily multi-threaded firmware, and I had no idea about what's going on. I have no idea on Android. So I gave up on this pretty quickly and said, well, it's probably just the fragmentation exploit described within Blueborn, because this device was definitely vulnerable to this. However, short before I left CMO, we have retested essentially everything, and also the fuzzer I showed you against the S10e. And we somehow managed to crash the Bluetooth daemon also of the S10e. And at this point, I was really angry because I for myself got a new mobile phone, and it was the S10e. Basically, also because my old phone was buggy and it was old. And then you get the newest flagship from Samsung, and you just crash your Bluetooth daemon with random messages. So if you have a closer look here, we have finally also symbol names available, what is pretty cool. And we are dialing here inside the memory, inside the mem copy that is called by this reassemble and dispatch function. So the code that is called here is used for packet fragmentation or reassembly of those packets. And this is a quite straightforward process. So if you receive a packet, or if you want to send a packet that is longer than what's fit in a single packet, you have to fragment it. So you send a packet that contains part of the payload and just says in the length, this packet is longer. And the receiving side will then copy this packet into a larger buffer to keep space for the continuing data. And if the target receives the continuation packet, it will just append the payload to this buffer. If you have a look at the code, and what you can also see here in the crash report, x2 is like the third argument, and this looks pretty negative, and we are here in a mem copy. So we can also see here we have a mem copy with a difference in the third argument, like the length parameter. And if you really pay attention and roll all this number, you can see that this can become negative again. So we're performing here a mem copy with a negative length, and this is like a huge integer, and therefore we are performing a mem copy in an endless loop, and this plane crashes. However, we also observed some different crashes on completely random locations, and we dug a little bit deeper, and there's in fact a pretty weird bug in the memcopy implementation of prior to Android 10. And to give you a short overview why this bug is really exploitable, what's happening is that the memcopy will not terminate in every case. There's an edge case where it will essentially copy 60 byte like a buffer underflow and like a roughly 80 byte controlled buffer overflow. So in one primitive, we have a memory leak and a buffer overflow, and this is a pretty strong condition for an attacker. So this bug we have also fully exploited to remote code execution. But again, we have disclosed this last November to Google. Even they needed the full 90 days for patching this bug. And the problem here is also there are some devices that only receive quarterly updates because your phone is too old. There are far too many devices that won't receive a patch at all. We are not sure about automotive. We don't have tested those devices. And there was even someone who ported this bug to 32-bit Android TVs, so those are broken now too. If you're interested in the in the full exploit write-up, you can follow the link here on the bottom. So finally, outcome and conclusion. Well, first of all, large-scale firmware emulation is possible. There might be even bugs that can't be found otherwise, like if you want to only fuzz a single handler, you might miss bugs. So it requires some effort, but it can be done. Some advantages we think from our approach is, first of all, we are using the same abstraction layer for developing the emulation as a code developer would do. So we're writing C code and not, for example, Python code to perform an API call to read memory, to parse it using Python structs, etc. What is a complete mess. We can directly dereference pointers, call functions, etc. And as we do not need Python calls to read memory, we can, for example, extremely efficiently traverse a linked list. So there are some cases where you actually want to do something with the firmware, and this is more performant if you do it directly in the code itself instead of using API calls. And in addition, your code can be partially reused to patch the device. So, for example, the heap sanitizer that we have developed in the emulator can directly port it to, or is ported to the device, so we can execute it directly on the chip. One big disadvantage is, well, the process is tedious, it remains tedious, but hopefully it's a little bit less. Down here you have a link to our repository, including all the write-ups. And now I want to thank you for your attention, and I would be hopefully open for questions.